Hello, community! So great that you are back. Have you ever thought that you could place an AI agent on a molecular level? No? Then welcome! We have some brand new ideas about AI swarm intelligence. Never mind that we're going to talk about a protein structure. This is applicable to almost any application when you use AI. Let's start, and hello to my channel Discover AI. We have a look at the latest research paper, and today is absolutely breathtaking. Because we will move here from our huge AI monoliths here to distributed cellular intelligence on a molecular level. You know, swarm intelligence, this is here familiar. If you just put in swarm here on my channel and you got multiple videos here 5 months ago. I showed you swarm agentic AI, great. But we have something completely new. This new swarm framework consists of 4 known components. A multi-agent swarm system, beautiful. A memory and a learning system, great. A structural evaluation unit, beautiful. And a decision-making algorithm. This is it. We don't need more. Now, there are some particular tools, external tools in bioinformatics that we need. The first is OmegaFold. If you're not familiar with OmegaFold, here, July 20, 2022, this is here, beautiful, the paper we introduced, OmegaFold, the first computational method to successfully predict high-resolution protein structures from a single primary one-dimensional sequence alone. Unbelievable. The second real important paper here, Rosetta. Not the Rosetta Stone that you know from Egypt, but something much more intelligent. Rosetta, a script-based interface for implementing molecular modeling algorithm. So, if these are just tools, never mind, you don't have to understand anything about them, it's just an external tool. But the methodology is beautiful. But you know what? Finally, AI is doing something that we thought AI would do. Develop new drugs, develop new medicine, develop new understanding of the chemical compounds. So let's do this. You know, everything comes down to protein structure and protein structure prediction task. And we have different AI models that design those protein structures already. And you see here AlphaFold, yes, of course you know this. But look at the training time. This is about 1,400 TPU, tensor processing unit, days. So the training time is quite significant, no? But even if you go with diffusion models, you have 1,800 GPU days. So our AI monolith protein structures are just crazy. And they hit now a generalization wall. They struggle now to design for particular biochemical properties outside of their training distribution. Some exotic vibrational frequency or some non-natural symmetries that happen, or some novel folding topologies that emerge. And they say we cannot do this without some very expensive fine-tuning. So what can we do about it? Now, the idea is not more of the same, but we have to shift here from a pattern matching, learning a particular probabilities of a sequence structure via the tensor weight of a huge LLM, to a reasoning-driven optimization process where we use here an LLM and external tools and multiple agents in parallel. Now, just imagine that you have a double helix, an alpha helix structure, or any protein sequence, but not as a string, but as a dynamic grid of active AI agents. Now imagine that on every amino acid position that you have in a double helix, you just imagine you would put there a little AI agent with a little bit of intelligence. And then you let the system optimize. And the intelligence of this AI agent, that is now multiple, a swarm of AI agents, positioning and encoding here every amino acid position in this helix, they can make decision how to fold this protein, so how to act here on chemical compounds. Now, you know, amino acids, we have more than 500, but about 20 are really interesting here for the human body. So 22 alpha amino acids incorporated into the proteins, and you have here beautiful if you're just arginine, histine, lysine, and everything that you know. I just know it from German, but you know it in English, which is great. But now just imagine you have an AI agent at position 12 somewhere in the alpha helix. Now, it does not predict the next token, but imagine we would give this AI a complete different task. We would tell this AI, hey, you look around in your molecular space, you look at the other molecules that are real close, your neighbors in the 3D space. Remember, now we are in a folded geometry. You check the global energy score, and I'll explain what it is in a minute. You consult a memory of past failures, and then you come to the conclusion, hey, wait a minute, as a molecular AI engine, or AI machine, I should mutate from glutamate to lysine to stabilize here the alpha helix dipole moment. And you might say, what, we do physics? Yes, we do physics here in this video. Of course, it's about science. And then you have, since we're talking about a swarm intelligence, the very next agent in this folded geometric space, let's say agent at position 13 now agrees with this. Really important. There's no central commander. There's no central brain commanding them what to do and how to establish their communication pattern. It is just here a global order. And you know what? The global complexity is brought into the folding geometry of the molecular compound in total. So folding into a specific shape emerges now because of the, if you want, intelligence of local, semantically negotiating multi-AI systems at a molecular level. I think this is just amazing. It is breathtaking. I'm loving this idea. So this mimics now suddenly a biological multicellularity, or what you know from physics, cellular automata, where the local rules drive the global morphology of the system, but it upgrades here the local rule from a simple logic element to a high-dimensional reasoning engine, and this could be our LLM. What an elegant solution. So here we have it. We do have here a molecular compound, maybe a protein structure, and then we put here in our Gedankenexperiment here a highly intelligent AI agent on each position here of an amino acid and have a look how they start now to communicate as a swarm intelligence. And you see we have here a bundle of agents here, beautiful. And then everything, of course, has to come together somehow. We have an omega fold. This is our oracle. Here the three-dimensional structure is generated. And for the stability, we will have a Rosetta energy field where this will be the optimization landscape for the, if you want, test time scaling performance of our agents. Here we are. What an amazing publication. We are here at the Laboratory for Atomistic and Molecular Mechanics, Department of Biological Engineering, Massachusetts Institute of Technology in Cambridge. Then the Department of Biomedical Engineering at Tufts University in Medford, Massachusetts. And, my goodness, the Center for Computational Science and Engineering, the Massachusetts Institute of Technology. And you got it. Everything is here beautiful at MIT. And look here, an old fellow that we know. Beautiful. So we can expect some beautiful insights. Title. Yeah, okay, the title, Swarms of LLMs, Agents for the Protein Sequence Design with an Experimental Validation Phase, published at the end of November 2025 by MIT. Do you know that they build in a agentic regularization? Because they say, you know what, the swarm produces here particular linear sequences that are linguistically plausible, given here the linguistic complexity solution that an LLM can perform. But this means also that the LLM acts here as a strong prior, refusing here to place sequences that violate the internal linguistic grammar of biology. I never thought I would say this sentence, but yeah, it makes sense. So this prevents here some adversarial examples like hallucinated structure for invalid here molecular sequence that are often produced by purely numerical supercomputer optimization of proteins. But you know what is amazing? MIT did not just build this framework, did not just compute the framework, did not just give us the code, but they also built it, and then they took their protein that was calculated with this new methodology, and they put it under a spectroscopy, and they wanted to validate if what the multi-AI agent system built is really there in reality. So they did synthesize the peptides and whatever, but the effect is, yes, they could prove that the swarm, AI swarm design actually folded in this particular way in the real world. And I think this is something spectacular, and therefore we're going to have a look at this paper. So the swarm framework achieved a precise design of alpha helices, our beta strands, and our coils with a high fidelity to residue conservation pattern. If you're not familiar, never mind. It is just the optimization process is now working here on a protein sequence level. And I never thought we could use here a swarm of AI agents on a molecular level. But yes, of course, why not? It is just unfamiliar thinking. But yes, this is great. So, the swarm framework exhibits here strong adaptability in achieving here some physiochemical, some functional, and some multi-domain design objective for the peptide or a protein construction, such as matching a specific vibrational frequency distribution, designing here specific proteins with a metal binding pockets, and designing some proteins with multi-domain structures. If you want to see, if you do not have a PhD in bioinformatics, never mind. Never mind. It's okay. I explain everything in simple words. Yeah. Look, you start with this sequence and you achieve here the functional sequence here of this protein that you were looking for. So this means you don't have to go in the lab and just do hundreds and thousands of experiments. You can now use a multi-AI system to develop and check here stable configurations and how we calculate here the stability of the system. I'm going to show you in a second. Now, the absolute crazy, amazing, mind-boggling thing is you don't use a specialized AI agent. You know what? They went with a GPT-4 Omni, our grandfather, with a Llama 3, the grandfather of the grandfather, or even a European Mistral. And they said, yo, great. And they tested here a multitude of them. And they said, if you go with a real small model like a Grok 3 Mini, you know, they converge too fast. This is the pure exploitation phase. This is not really working. But what they found to be working real well is a GPT-4 Omni. They said this is already large enough reasoning model to have a little bit of a three-dimensional complexity and maintain a healthy pattern of exploration versus exploitation. And I thought, what an amazing idea. So on the base, we have an energy field, a Rosetta energy field. I'm going to explain this in 5 minutes. This is here the optimization landscape. If you're familiar with the gravity well example here from Monet, this is now also something like this. Here we have the protein structure that we are trying here to understand or to build. And then on every acid position, we place now here in our Gedanken experiment here a complete AI agent system. So we have here, I don't know how many AI agents, and they now form a swarm intelligence like a bee hive, and they communicate and they optimize. And whatever they come up with, they have that. This is just a linear one-dimensional sequence. No, everything is done in parallel, but we have to fold it in a three-dimensional space. And this is here where you see this main idea. This is how I built it in Nano Banana Pro. I hope it makes sense for you. Just wanted to show you all the linear sequences are then accumulated. And then here Omega Fold is this mastermind that really makes the dimensional jump here from a one-dimensional sequence. It folds it here into an energy, hopefully stable configuration of a three-dimensional fold of alpha, beta. And you know all of this. Great. And you know what? You know what is absolutely amazing? The AI swarm can find also solutions that are outside of the training distribution of the protein prediction system. So it makes a step beyond our classical protein AI systems. And it found here, if you want, de novo discovery of non-natural proteins. So it builds synthetic proteins that are not, if you want, happening here in the natural world. So this system seems somehow to work. So let's explore this in more detail. Okay. 3 strategic insights. There's a lot of technical detail in the paper. But if you're not familiar, never mind. I give you the overview. I give you the feeling, how it feels. I give you the core idea. You know, all the AI industry is going here to larger and larger models. And now we say, well, a year ago, Well, what about scaling the test time compute? What about test time scaling optimization? You know, this reasoning model take half an hour before they give you an answer. And now they apply this simply to biology. And what is mind-boggling is that you can do this with an AI system, an off-the-shelf AI system, without training here a domain-specific model on bioinformatics. And you might say, how is this possible? And the solution is simple. Do you know what? The second insight, this swarm framework requires 0 gradient updates. There is no reinforcement learning. There is no whatever. There's no additional training. And it's shown to be a superior strategy here, which is just amazing. And unlike also, we have a lot of diffusion models, not only a transformer model, also dual fusion architectures in AI, which often require complex differentiable guidance terms here. This simple swarm intelligence handles here everything with a linguistic logic-based objective. And this objective function is, you're not going to get, is our natural human language. And reading this is absolutely unbelievable. So let's have a look here at the AI swarm optimization engine, because of course, you know, this is a mathematical process of optimizing your system. We do all the AI calculation in parallel for each little agent sitting here on a molecular position of an acid. So therefore, everything has to happen at the same time. Yeah, beautifully. Look, an Apache 2 license, we have everything here. Protein swarm, this is the GitHub repo for you. You have the analysis, the examples, you have every framework that you see here. Folding utility, the distant matrix analysis, the design loop, the memory system, everything is available for you. Project structure, clearly, absolutely beautiful. You have the folding utilities, the structure evaluation, the Rosetta energy utilities. I'm going to talk about this in a moment. The LLM monitor, and you have everything that you need for the protein folding. Let's jump into the technical part. If you don't like, okay, I'll say thank you for watching. If you're a little tiny bit interested in how we can do this here on a technical level, how do we implement this with a multi-agent system, welcome. This is not a technical part of the video. So again, simple visualization with NanoBanana Pro. Took me about 15 minutes till this stupid machine could finally build what I wanted the machine to build, but here we have it. Here is our protein complex in the middle, no? And then I've chosen here a representation for each. Let's say we have 50 agents here. They are here in this circle, and they are here this glass panel. And you see we have here Python Rosetta is calculating here different Python functions beautifully. But those here are now really calculated on every and each position here in the, let's say in the alpha, here really the 3D folding structure and the energy optimization and everything. So those are these laser lights, so you see exactly this is here an agent that is located exactly here in the alpha, and yeah, you got it. And here we have at the bottom here the fitness landscape mapping here, the energy potential that we use for the optimization of the system. You see we are here at phase 2 of the omega fold inference run. We have Rosetta energy, global memory buffer. Yes, I have to explain this. So in the middle, protein ribbon structure as familiar. 50 vertical transparent class interface plate. These are our 50 agents. Those are the attention vectors, if you want, crisscross, connecting here the blades to the specific atoms in the protein, having visualization of the spatial neighbor context. Remember, we have a linear, if you want, environment context, and we have a folded geometry. So we have multiple systems to take care of, plus the base of the hologram, as I told you, a 3D topological surface, the wireframe mesh here, representing here the fitness landscape for the energy optimization. And then this is it. So let's have a look. Architecture. Each residue position is assigned an autonomous agent, and the framework operates here in multiple rounds. So for each single step, each single agent, A sub I receives a highly structured context vector. C for context, A for the agent. And in this context vector, we have now, if you want, everything that is needed now to make a decision. We have N, our linear neighborhood. As I told you, we have a linear structure, of course, with all the residues. Then we have the folded spatial neighborhood and a 3D complexity fold structure. So you can calculate the difference between the molecular compounds and say, what is the van der Waals, what is here the hydrogen bridge, and. Then, of course, we are in a wet environment, solvent exposures. We calculate here, we integrate also the defined secondary structure of the proteins, the DSSP, and this is really important, a memory function. So all the history of the past mutation at this particular place, at this particular amino acid or whatever, at this position and this impact, how did the energy fluctuation, the energy function change? Was it a stable solution? Yes, no. If not, we collect our failure modes so we don't make the failures again. Nice. And then we have, as I told you, every AI is more or less just a mathematical optimization. Let's enter the optimization loop. Let's call it a semantic genetic algorithm at molecular level. We have 4 phases. The first is the agent collects here the data. We have a parallel inference run of all the agents operating in parallel. Outputs here a mutation proposal, says, hey, I want to change my medical compound because I think given in the position I'm sitting here in this 3-dimensional alpha helix, I think I want to change here my chemical compound to a different amino acid. The system collects all this proposal from all our agents in all the different places and generates a sequence vector. And then, of course, we have the proposed sequence is constructed and the framework employs now omega fold here as this differentiable structural oracle to go from a 1-dimensional linear sequence to a 3-dimensional coordinate, a real folded protein structure. And yeah, this is simply the task of omega fold, the structural oracle. But then if we have the folding, there could be that there was an hallucination by the folding AI, no? So therefore, they make sure we just check, we just check the energy and the objective evaluation. So the generated 3D structure here is evaluated using Rosetta. This is not the Rosetta Stone. Again, this is a physics-based energy function and our DSSP. So again, minimization. The total energy function is minimized. This is now here multiple term energy function. And you are familiar, hopefully, with these terms from theoretical physics here. Yeah, more or less molecular mechanics, no? And then we have PyRosetta, our Python program, loads here from the protein database, calculates the pairwise interaction graph, and simply sums up the energy terms. Couldn't be simpler, no? Plus, wait a minute, it does something in addition. It calculates an objective score. This is simply, if you want, the percentage similarity to a target vibrational frequency spectrum. If you're not familiar with this, DSPP holds here secondary structure of the proteins. This is here since November 2010. Availably, Oxford Academic, Nucleic Acid Research, here everything for you to read about. And yes, I know if you say, hey, can you explain the 4 physics term here? Of course, the first here is van der Waals forces, so you know this. But I want to stress here, I put in addition here this warm relevance here of van der Waals forces. So if an AI agent blindly mutates now a small glycine to a large tryptophan in a tight core, this van der Waals forces will skyrocket. No? This system will detect this spike and reject here this particular mutation from glycine to tryptophan immediately. What a beautiful solution. Second, hydrogen bonding, H-bond. No? Interaction between the donor hydrogen atoms, you know about this warm relevance. The agents are often tasked with creating alpha helices, no, of course. But while the LLM might suggest this sequence using alanine, the Rosetta confirms that the geometry predicted by omega fold actually forms the necessary hydrogen bond to keep this alpha helix stable. So we do have, if you want, omega fold and Rosetta here, Rosetta in particular here as an evaluation tool. Then we have the electrostatic forces here, ALEC, Coulomb interaction. You know this, but this warm relevance is that if an agent places 2 positively charged molecular compounds next to each other, they of course repel. No? So Rosetta forces this warm to optimize for the charge complementarity. Such an elegant solution. And then a reference energy. This is simply represent an energy cost of an amino acid in the unfolded state. So it acts here as a chemical potential, preventing the model from just filling here the protein place with the cheapest amino acid, like alanine, by balancing here the amino acid composition distribution itself. And this is it. And now we are up to phase 4. The last one is simply an optimization, a gating or a greedy hill climbing here with a memory update. So, as I told you, greedy hill climbing strategy here for a decision function. And the decision function, should we accept this, what comes out here of omega fold here as a true new optimized protein structure is simple. 2 cases it's true, and 1 is false otherwise. So true is if the objective score is greater than of this new structure than the objective score of the old one, and if here the energy of the new one is minimized, so more stable if you want than before, and the objective score is stable. So 2 simple add functions, end functions here in Boolean logic, and you have the acceptance here of this new 3D folded geometry. As I told you, the memory records any failure. So this prevents, if you want, the swarm from exploring here the same data end twice. And the warning entry now in the memory can be like this warning: hey, little AI agent at position 212, you tried mutating here lysine to glutamate already in step 35, and it was rejected due to clashing with some energy optimization or whatever. Do not try this again for this particular configuration at this particular point and place in time in the alpha helix and other configurations. Great. Okay, Rosetta. Not the Rosetta Stone, but Rosetta, simply now used again to fix the hallucination problem of neural network. And you know, OmegaFold is a massive AI system. So yes, OmegaFold can hallucinate. And now we use Rosetta only for the, if you want, evaluation and elimination of any hallucination that happened during the folding process. Why? Again, OmegaFold predicted here this higher complexity is a deep learning model, predict a beautiful helix shape for a sequence that physically should not fold that way, a false positive. And Rosetta, if you want, is really now the theoretical physicist that calculates now in detail the energy of that specific sequence structure pair. And if OmegaFold hallucinated a helix, but the atoms is crashing each other, Rosetta simply says, hey, we got such a high peak here in the energy score, so I can reject this here. And the swarm uses here this discrepancy to reject the hallucination. It knows this is not a physically valid folding by OmegaFold. Great. What? We have additional insights? Yes, of course, we have additional insights. Take a step back and look at the complete system complexity and the system dynamics. What is it? It is not just an LLM. It is not just a multi-agent system. We have built MIT has built a hybrid neurosymbolic system with a heavily tool-augmented AI system that we say let it play at a molecular level. The LLM acts again only as a semantic function, not as the AGI super hyperintelligence. We don't need this. We can go with a grandfather GPT-4 Omni system and we get results we had not in any supercomputer simulation. The LLM only as an old-fashioned semantic reasoning core in natural language, but, and this is a big but, of course, the best supercomputer tools that we have, specialized external, let's call it sensors or tool or whatever you like call it, the best OmegaFold engine, the best secondary structure of protein, the best protein database, the best energy landscape optimization algorithm for Rosetta to perceive here the reality. So there's a lot of intelligence out there in our tools. Tools can be everything, as I showed you here. And the LLM, we don't need a super intelligent LLM. We just need a semantic reasoning core that understands here basic bioinformatics. I would like to show you in a simplification, a dialogue here in this warm approach here. No? The LLM is now just the executive, not the hyper-intelligent being. So the executive LLM says, hey, Now, my job is more or less to stabilize here this particular local area of a helix structure, alpha helix structure. Let's try, for example, to have here a point mutation here to tryptophan. Then Rosetta, being the theoretical physicist, the engineering, the validator, said, wait, tryptophan causes here a massive energy spike. This means a clash here from a stability point of view, a frequency point of view, an eigenvector point of view, whatever there is. If you know bioinformatics, you do know exactly what I'm talking about. And then the executive LLM, the job is, oh, understood. Okay, I will revise my strategy. So let's try alanine instead. This is the whole job of an LLM. Simple old grandfather GPT-4 Omni. But, another big but, if you think about now the structural complexity of the complete AI multi-agent system, what have we done? We have done exactly the same what I showed you here in this video about cybernetic AI. We do have a cognitive tensor field. Remember, this is part 2 of the dual manifold AI video. But we have the intelligence more or less outsourced here to the tools that we need for this particular job. And the LLM itself is just a semantic transformation engine. It doesn't need to be hyper intelligent at all, because we do have deterministic tools that are much better than even the, I don't know, hyper super AGI LLM. One word where I say an optimization is necessary, the current implementation here relies here on the folding step, this omega fold 3D folding. This folding, think about it, if we have a lot of local information, but we have no global information, omega fold provides here, propagates here the global information as a structural folding, a geometry folding of the space, which is a smart workaround, but if you will further optimize this, I think further versions here might need more advanced optimization methodologies. But hey, what do I know about graph topologies? Performance, the results. I only showed you this. Here, if you train here AlphaFold, about 1,400 TPU days. So if your name is Google or, I don't know, MIT Medical, you can do this. Yeah? But look at this, the swarm network here from this paper, there is no training required. We go with grandfather GPT-4 Omni, and the inference time per prediction is just a few GPU hours on a non-domain specific, non-trained LLM. Can you imagine what this means here for generating new configurations? I love this study. Okay. Performance, and here I just quote here the authors because they know so much more than I. The swarm AI here explores complete novel region of the sequence space. Have a look at the paper. There are some beautiful visualization, but a little bit too complex here to present it here. And if they go for the benchmarking data, you find all of the benchmarks in the paper. Benchmarking against state-of-the-art protein engineering methods, including structure prediction model, autoregressive protein language model, and all the diffusion models that I just showed you. They highlight a simple result. This new swarm framework strength is precise design control of the proteins, adaptability on the fly, no extreme training process, and a multi-objective optimization given the functional structure of our new proteins. Absolutely amazing. And here we are. This is the end of the video. I hope you had a little bit of fun. Never mind that we went here to bioinformatics here about protein folding. You can take this idea to put agents wherever you want, have them work together as a swarm intelligence, and just be absolutely amazed by their result. I hope you enjoyed it. Maybe you want to become a subscriber, maybe you'll become a member of my channel. Anyway, it would be great to see you in my next video.